Today's lecture is about Octave, specifically how to use Octave to solve a pretty complicated problem. So the problem we're going to look at is to try to do a simulation of the game of craps. So what are the rules of craps? Well, craps is played with two dice, and you roll the two dice. So when you roll two dice, the result, you add the two numbers that you get, and the result is either a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or a 12. You can't get a 1. If you can get two 1s or two 6s and anything in between. Now there's multiple ways to get like the number 7. You can get a 1 and 6, 2 and 5, 3 and 4. So different outcomes will occur more or less frequently than other outcomes. So what are the rules of the game of craps? Well, it's a little complicated, which is what makes this an interesting computer program. So if you roll the dice, and if you get a 7 or an 11, then that's an instant win. So you've won the game on one shot, just on your first roll. However, if you roll the dice and you get 2, 3, or 12, then you have an instant loss. Now, the game is over and you've lost right away. What makes things interesting is what happens next. Well, what if you don't get one of those 5 outcomes? What if you get something other than a 2, 3, 7, 11, or 12? Well, what you do is you repeatedly roll the dice until you get your first number, which is X, or 7. So X is what you got on your first roll. So let's keep track of that as the variable X. So if you don't get 2, 3, 7, 11, or 12 on your first roll, let's say you get a 10 on your first roll. So suppose that X is equal to 10. Then you keep rolling the dice until either you get another 10 or you get a 7. If the 7 occurs before the 10 occurs, then you lose. If the 10 occurs first, before you get a 7, the game's over and you win. So how do we calculate the probabilities of winning the game of craps? Well, you can actually do this theoretically. It's not too hard, but it does take a little bit of math. But in real life, things are often so complicated that you can't analytically calculate them with formulas. In calculus class, we like to assume that everything can be done, simply by hand. But in real life, problems are much more complicated, and often you need computers to try to guess the answer. So that's what a simulation is. We're going to try to simulate reality, and we're going to have the computer play the game of craps 10,000 times. So it's going to play the game of craps 10,000 times, and we're going to keep track of how many times we win. And then we'll be able to figure out the probability of winning in the game of craps. Now, along the way, we're going to review some important Octave constructs we've learned to get us ready for some of the new Octave programs we're going to be doing before the end of the trimester. Some of the things that you'll see here are the use of random numbers, the use of arrays, for loops, and conditional statements, and Boolean variables. All of this is in this one program, and as you'll see, it's going to be a bit more complicated than the usual 5-line programs we do. Also, after we figure out the odds of winning a game of craps, we'll figure out the odds of rolling each of the individual outcomes, 2 through 12. So we'll figure out those 11 probabilities and see which numbers come up more frequently. There's a reason that 7 is a special number for this game, as you'll see from the probabilities of from the probability of obtaining a 7 in the first place. So if you need to, you can pause this video and look up the game of craps if you're confused about how it's played. There may be variations on the rules, so you might have to go back to our description here to see our exact version of craps, because there might be different versions out there. Alright, so let's go through this program. So these first lines here, they are comments. Octave ignores them. It's as if they do not exist at all, but we keep them there so that we can understand what the program is doing, but they have no meaning, of course. Okay, line 7. This tells Octave, format long, to use to display our answers with a lot of decimals. Okay, so n is set equal to 10,000. We're going to play the game of craps 10,000 times and see how many times we win out of these 10,000. Okay, first roll equals zeros 1 to n. 1 comma n, sorry. So all we're doing here is declaring an array, right? We're just declaring a list of numbers, and just to see some quick examples of this, if we say x equals zeros 1 to 5, and then we display x, see, we get a list of 5 numbers. And then, of course, we can fill in these numbers. We could say x of 1 equals 2. And there's x. X of 4 equals 7. X of 5 equals minus 2. X of 6 equals 3. Well, what did it do there? It simply added another element to our array. It appended an extra element. It made the array a little bigger. Now, what if we try x of 10 equals 2? So it adds zeros for the missing numbers, and it makes sure that the 10th number is a 2. All right, so that's a quick review of arrays. So n is 10,000, but we're not going to put a 10,000 throughout our program, because let's say we want to change this and run it 1,000,000 times later on. So good programming practice would be to set your constants at the top of your program, and then use the constant variables as in your program so that when you change one line, it'll change everywhere. All right, so number of wins is 0. We're starting out by saying there's no wins. We're counting the number of times we win the game. Okay, here's our main for loop. This for loop goes from line 13 to line 52. So this is the meat of the program, is within this for loop. Now, this is something new that you haven't seen. So our for loop, of course, is going to go from 1 to n, 10,000 times. Flag is what is called a Boolean variable. A Boolean variable can have two outcomes, either true or false. So we're going to use it. It's a flag. Imagine it's like you have a flag and you're using it to tell people to go or to stop. That's essentially what this flag is going to do. Depending on whether flag is true or false, different things will occur in the program. We don't have to use this type of construct, but since we don't have more advanced statements, we're forced to sort of do things in a primitive way. So using this flag is a bit primitive. There are better ways to write this program, as I'll show you next. But this is an easy way to do the program with things that we know already. All right, so flag starts off as true. Okay. So first step is, let's roll the dice. So this statement rolls the dice. Now how does it roll the dice? Well, let's review a little bit and look at this randy statement. So how to use the randy statement. It stands for random integer. So rand I of 6. And let's keep calling the randy statement. See how it gave me 4 2s in a row? That's just random chance. Then it gave me a 6, then another 6, then a 5, then a 2, then a 6, and a 4. You see, it just keeps giving you a random number between 1 and 6. In fact, you put the randy inside a for loop and do this a little bit more efficiently. So for I equals 1 to 20, rand I of 6 and 4. And that's calling the randy function 20 times. So as you can see, this is called a uniform distribution. The numbers 1 to 6 are all equally likely to occur. So this is what's called a uniform probability distribution. All right, so back to our program. So when you roll the dice, we need 2 dice. So you have to roll the first dice. This is the result of the first dice. This is the result of the second dice. And when you add them, you get the result of the roll. So our first roll is called X. Now line 16 here, we're storing the first roll in an array which we called first roll. So the first row, I is 1. Second row, I is 2. Third row, I is 3. It's a little misleading. When I mean first row, what I'm thinking is subsequently we may have to repeatedly roll the dice to win a game. So this is just the first roll in each game. Okay, so we rolled the dice, we got X. Now we're just storing X in the array first roll, position I. Okay, now remember, if X is a 7, if we rolled a 7, then we won the game right away. So what we do when we win the game is we update the variable num wins, and we just add 1 to whatever it was before. When we first start off, it could be 0, but it's not going to be 0 for long. Each time we win, it's going to increment by 1. And then I'm saying set the flag equal to false. I can't explain this right now why we're doing that. You'll have to see a little bit later how we use this flag to understand why. But basically, it means we're done with this game. Once the flag is set to false, the game is going to be over and we're not going to roll anymore. So that's a hint as to how we're going to use this. If X is an 11 on your first roll, well, we won again. So number of wins is updated, incremented by 1. Now if X is equal to a 2, or a 3, or a 12, we're going to lose instantly. Notice here, we don't update number of wins. We just keep it the way it was, and we do not increment it. That's because we don't want to count the games that we lost. We're not keeping track of specifically the games that we lost. We're just only counting the games that we win. Okay, now here comes the interesting part. This little while loop right here. So a while loop will keep running until the condition is false. So the nice thing about Boolean variables is we don't have to say something like while this is equal to that. You can simply say while flag. Flag is either going to be true or false. So if flag is false, this while loop is never even going to run at all. So the only way that flag can still be true, remember, it started out true right here. We're still inside the for loop. But every time one of those 5 events occurred, flag became false. So if none of these 5 ifs are true, then flag will remain true. So let's assume flag is true for the moment. Roll again. Y is our second roll. If Y is a 7, we lost. The game is over according to the rules. Remember, this is our second roll now. So we set flag equal to false to say that we're not going to be rolling anymore, and the game is basically over and we lost this game. However, if Y is equal to X, so what this means is if our next roll, if Y, which is our second roll, is equal to our first roll, then we win the game. So we update the number of wins, we increment it. And let's say none of these two options occur. Suppose both of these if statements are false. We didn't get a 7, and we didn't get our first roll again. It didn't repeat yet. Well, flag is still true, right? It never changed. So as long as flag is still true, it checks it. Yes, while flag is true, do this loop. So it rolls again. Y is reused, and that's now going to be, say, your third roll. And you would keep doing this until you either get a 7 or your first roll. All right, so eventually the probability is 100% that the game will not go forever. You might think a game could go forever, but the probability that that occurs is 0. It can be shown mathematically. Eventually, it will happen. It may take 100 years, but the odds of that is, it's more likely that the sun will spontaneously explode than you'll play a game of craps for 100 rolls in a row. Things like that occur. So the game will end. Okay, so this while loop, you've done with the while loop. Finally, flag will be false, and you won't repeat it, and you'll go right to here, and you'll end your for loop. So now, remember, that was just your first game. This whole discussion was just about our first game. So we go back up to here, and now I becomes 2. And it repeats the whole process again. Notice number of wins and first roll, these are outside of the for loop. So they're not going to be overridden. They'll keep their values throughout the entire process. All right, so the for loop is done. We've just done it 10,000 times, say. And now let's look at the answers. Okay, so we'll print out, this is a string. Remember, this is just words to print out. But here's some math. We're printing out the number of times we've won divided by the number of games. So this is the probability of, and this is essentially the probability of winning the game of craps. It's the percentage, the running total of how many we've won over how many we've played. And this is the empirical way of estimating the probability of winning on a single game. Okay, so we have the number of wins over the number of games, and that's the main answer we're looking for. So let's run this program and see what happens. So there is a way to run programs without opening Octave. You'll run it from within Octave, but I'm having a little trouble on the Mac version of Octave, so I'm using the command line. So Octave command line interface, I call this crapseasy.m. Takes a minute. Octave is a bit slow. In fact, it's a very, very slow program. You wouldn't want to use Octave for high computational, long computational programs. But it's good for small things and for teaching purposes. All right, so this is the output. All that was to get this number. The probability of winning a game of craps is 0.4929. So that's if we run it 10,000 times. Well, if you want to see 1,000,000 times, it's going to be a little bit longer, but or 100,000 times, say. So we update n to 100,000, and let's run it. And as you can see, here's Octave running. This computer has 8 logical CPUs, so it doesn't tax the computer much, but it's only running in one thread. It's simply using one of the 8 CPUs here. You can make this program 8 times faster on this computer by splitting the for loop into 8 for loops and having them run all at the same time. That's called parallel computation. But that would take some extra time and a lot of effort, and is not worth it here. And there are much better programs for doing that sort of thing. All right, so it's going to take a little bit. Perhaps we'll come back to it when it's done. Now, remember how we were storing the first row? So we said the first row is a list of n numbers, and then in this line right here we actually stored it. We stored the first row, but not any of the other rows. We never stored anything else throughout the for loop, only in this line. All right, so this contains our first row. All right, so it looks like the program finished. And this is a pretty fast computer, but as you can see, it still takes a bit of time. So the probability is 0.494390. All right. So you can look up the actual probabilities online, and you'll see that that's pretty close. Okay. Finally, let's see about this first row array. So we're storing the first row in each game. Okay. Now the place that we use it is down here. So from this point onwards, we're going to use it to figure out the frequency of obtaining each of the outcomes from 2 to 12. So how do we keep track of how many 3s we obtained, how many 6s we have obtained, how many 12s, how many 2s? Well, it's actually very, very simple, though it's a bit tricky to understand. So this is the line that basically counts how many 3s and how many 4s were obtained throughout the entire process. So first we need another array, another list, and this is a list of 12 numbers. Started out as 0. So first it starts as 12 zeros. 1 through 12 are the array positions. Okay, so now we go through every one of our rows, all 10,000 of them, and if you look at the first row, let's say that's a 7. So we're saying in the 7th position of the array count rows type, increment whatever value is there by 1 every time a 7 occurs as the argument of count rows type. So I said it would be a bit complicated. It's so simple to write, but it's a bit complicated to explain. So let's try again. So first rows is going to be any number between 2 and 12. We don't know which one it is, but there's 1,000 of them, and they're all numbers between 2 and 12. So let's say it happens to be a 5. So the shaded value is a 5 now. Same thing here. This is a 5. So the 5th number in this list is equal to its previous value, which is at least 0, plus 1. So this effectively will count the number of 5s and all the numbers as you go from all 10,000 of the rows. It's sort of like you look at the ith row. So this is the ith row. And see what number it is. Whatever number it is, you go to that position in this array, which is only 12 numbers, and you say, now I have one more. So we add one more to our running total. All right, so we've split our 1,000 rows into 11 different bins from 2 to 12, and we have now the count of how many 7s we got, how many 3s we got, how many 2s. So to figure out the frequency and the probability of obtaining each row, we simply divide by n, which is the number of total rows. So let's look at the answers for that. So after we get our winning craps percentage, we have a 0.02716 probability of getting a 2, 3, and let's take a look at the 6, 7, and 8 here. So this is where things get interesting. You see the 7 has the highest probability. And you could probably guess that this answer is 1 out of 6. It's actually 6 over 36 if you look at the sample space. And the probability of getting a 2 is the same as the probability of getting a 12, because there's only one way that can occur. But there's 2 ways to get a 3. So 0.561, and there's 2 ways to get an 11. These numbers are supposed to be exactly the same. But as you can see, they're not exactly the same, because random chance is not the same thing as the theoretical answer. The random chance will get better and better, but it won't give you the exact answer. It'll start to approximate the true answer. All right, so this concludes this lecture. Please follow the additional instructions in the email.